I don't think by any means this is exhausted. There are always things. And one thing I forgot to mention is like there could be more than one mechanism operating, right? Of course, if F is very low, like we had in gauge mediation, the contributions from gravity mediation will be very small because they all go like 1 over m Planck suppressed, so it will be F over m Planck. And for F as low as we needed for gauge mediation, the gravity mediation contribution will be very small. But in principle, it will be there. If you are willing to accommodate non-renormalizable theories, and I think we should, then that contribution will be there, but it will be small. So you can have more than one contribution appearing, and then the effective terms that are set will be some combination of them. So that is something which I wanted to mention last time, but I forgot. Anyway, so today I will talk about electroweak symmetry breaking. So what are the conditions required in order for electroweak symmetry to be broken, which we know we have to have, right? Because the gauge bosons are massive, and so we need to break electroweak symmetry, and supersymmetry has some nice aspects to it, which will let electroweak symmetry breaking happen. So we already saw that MHU squared runs negative when you run from a high scale, and so without doing anything, just having the top large like we must to match with experiment, it implies MHU squared will be turned negative at some low scale and will trigger electroweak symmetry breaking. So this happens very naturally and is a very nice feature of supersymmetry or MSSM, if you will. But we'll see there is one big problem to this whole thing. We'll come to that. But let me start talking about electroweak symmetry breaking. Everybody knows what this notation is, right? It is just electroweak symmetry breaking. So what conditions do you need in order for electroweak symmetry to be broken by the vacuum? So remember, it should be spontaneously broken, right? We don't want to introduce any explicit breaking of the electroweak symmetry. That will spoil renormalizability and also, so we don't want that. So let's start with the potential involving the Higgs field. I'll tell you in a minute why it's sufficient to look at only the neutral. So let's write down the potential. So remember, we are writing all of these at the low scale. So we can, some mediation mechanism will set the boundary condition at the high scale, and then we can use RGEs to run it down, and then we are asking what conditions might it satisfy at the low scale. So this is involving the neutral fields. So the charge fields are not shown, so you can always use SU2 left invariance of the Lagrangian to set one of them to 0, set HU plus web to 0. Right? The whole thing has an SU2 invariance, so you can use that even if there were a non-zero value, you can just use that rotation to set this to 0. Then show that for that minimum to happen, HD minus has to be 0. So, and therefore, at the minimum, the charge fields don't get away. And this is good because EM is unbroken. If this were not true, then there would be minima which would break electromagnetic charge, and we don't want that. Right? So this you can show. Therefore, we have not written the charged fields. So you just now consider the neutral fields, and then you ask, what is the minimum of the potential involving the neutral fields? So we are asking for webs of these fields at the minimum. So another thing is, without loss of generality, you can take B mu real. So this parameter B mu, right, we can take that to be real. Since if this were to have a phase, you can just rotate one of these fields. Let's just say we pick this and rotate this in order to absorb that phase. And you can see none of the other terms are sensitive to this phase. So you can always absorb away the phase of B mu. So then minimum for HU HD. So I'll stop writing the 0 on the field. So since I've dismissed away the charge field saying that the waves have to be 0, I'm only talking about neutral fields. And so I'll just omit the superscript 0, but I'm talking about neutral fields, right? So minimum for HU HD is such that HU HD is real. This product is real. So each can be taken to be real. So if this has to be real, any phase in this and the phase in this should be opposite, right? And so because this also have hypercharge opposite, you can use the hypercharge invariance in order to get rid of the phase. So that is a statement that you can take each one of these to be real. So in the MSSM, CP is not spontaneously broken, right? So the phase is not physical of the web. So you can always choose the webs to be real. In other words, CP is not spontaneously broken. Okay, so we'll continue and ask what conditions are necessary in order for that have to be satisfied at the minimum for there to be a non-trivial minimum also. So the minimum, so look at the D flat direction It just means that something where this goes to 0, this is the D term, right? So this whole thing is the D term. So if HU equals HD, so I'm not putting this thing, but now whenever I say these things, I mean the web, right? So, yeah. Yeah, HUHD should be real. So if this has a phase, this has to have opposite phase. But they also have opposite hypercharge. This has hypercharge plus 1/2. This has hypercharge minus 1/2. So you use hypercharge invariance. The whole potential, Lagrangian, everything is hypercharge invariant. So make a hypercharge rotation. So since it's an invariance, nothing will change. So by making it, making the appropriate angle, you can get rid of the phase. So let's say this had phase theta, you make hypercharge with minus theta or minus 2 theta, because the hypercharge will give you 1/2. So it will put an opposite thing and will absorb away that theta. And this has to work for this because it has opposite hypercharge. So that will also absorb away the phase. So in other words, it will leave the whole thing real. So you can just make it real. Another way of saying that is the phase of this is not physical, because you can just redefine everything and the Lagrangian will not change. So it's just a spurious thing. You can get rid of it. In other words, you can work with a phase, and any physical observables you compute should be CP invariant. So you might as well use this argument and get rid of it right in the beginning. Or you can work with it, but it will not lead to any observable. So look at this D flat direction. So that certainly will minimize the potential, right? So it will be, if these are equal, this whole thing will be 0. And so this will not constrain the waves, right? So such things are called flat directions. So I can go in this direction as large HU and HD I want, and it will not constrain. But that's only looking at the D term. The other things, of course, will constrain it, and that's why it is called a D flat direction. So just the D term has a flat direction in this thing. So just look at that direction, and you can argue that for that to be bounded in this direction, for it to be bounded from below, it will impose a non-trivial constraint. So I'm just taking this from Martin. You can check that this should be true. So the claim is that if this is not satisfied, the potential is unbounded from below, and then you will have a runaway vacuum. So that's not acceptable. And so that will impose a non-trivial constraint on the parameters. So these are the kinds of things that we want to derive. So what are the constraints if you have to have a well-behaved potential? And so the other condition is for electroweak symmetry breaking to occur. In other words, the HU and HD have to have waves. If these don't happen, then electroweak symmetry will not be broken, because then no field has wave, and then you are not breaking the symmetry. So the condition required for this to happen, again, you can convince yourself that the condition required is that condition has to be satisfied. So it is putting non-trivial requirements on B mu, right, from both sides. So you see that now if you have a particular mediation mechanism which sets some values at the high scale, you can use RGEs to run it down at the low scale, and it will put a non-trivial requirement on that theory that but for electroweak symmetry to break, these things have to be satisfied. So this can rule in or rule out models of electroweak symmetry breaking, or models of supersymmetry breaking, sorry. So of course this is required to give masses to W and Z. So let's take the common convention is to take the wave of the up type as Vu and the wave of HD. So these are all, remember, neutral, right? So Vu and Vd. And then to get correct W plus minus and Z masses, this quantity Vu squared plus Vd squared, which is just V squared, should be so I'm just using Martin's convention here, where he takes V to be 174 GeV. The other common thing is to put a square root of 2 and then take this as 246 GeV. So they differ by square root of 2. So just keep track of the convention that people are using in defining V. So of course no content changes, it's just a convention whether you use 174 or 246. And then one defines this tangent beta, which is Vu over Vd. So you're just trading parameters instead of using Vu and Vd as the variables in your theory. You can redefine them and talk about tangent beta and so on. It's just convenient for various reasons, so it's just a convention that people use. So this you will see very commonly stated, right? All of the supersymmetry plots, anytime people present anything, will be as a function of tangent beta and so on. So this is just the ratio of the waves. So dV dHu equals 0 implies, so let me just write, and dV dHd. So the potential should be minimized with respect to Hu and Hd, and this will mean mHu squared plus mu squared cotangent beta and Z squared over 2 cos 2 beta. And HD plus mu squared minus V mu tangent beta and V squared over 2 cos 2 beta. So again, this will put non-trivial relations among the parameters. So using these, you can trade parameters. You can just say that, okay, this is an absolute required must, so I will just impose this condition on the theory. And you can just trade parameters using these theories, these equations. And just rewriting these, you can write it of the form So you can write these two relations. Of course, mz is defined as usual, like v times square root of g squared plus g prime squared with some square root of 2, 4 factors. That's the same definition of mz. And you just plug that in and then trade these. So you can just rewrite these equations to be that. Now, the reason I wrote this is that this is very telling, this especially this relation. If you look at this thing, so this is fixed by experiment, right? This is of the order of the Electroweak scale, 91 GeV. So we know mz. So whatever these parameters have to be, they should in the end give you mz, the correct mz. Now, this is a bizarre relation because all of these are SUSY breaking parameters, right? These are things that we added by just like soft breaking terms into the MSSM Lagrangian, or in some more fundamental theory, they came in as the result of supersymmetry breaking by the F term that in the examples that we saw. But this thing is the mu parameter which goes into the superpotential. It's not a soft breaking term. But this is saying in order for cancellations not to occur, mu should be roughly of the same order as the MHU squared and MHD squared. U squared should be of the same order. No, but it is completely bizarre. So why should some supersymmetry preserving superpotential parameter be of the same order as the soft breaking term, the SUSY breaking term? And we saw that that the dynamics that is involved in all of these things is very different from that, and so there is no reason a priori that they should be related. But this condition demands that if there is to be no fine cancellations, of course, things can be such that you pick mu some value and you pick some model or nature is such that m squared comes out to be the same high value and they cancel and so on. Those things can happen. But it is very hard to see why unrelated parameters should have this aspect to them. So this thing is termed as a mu problem. So this, I would say, is aesthetically one of the biggest problems of the MSSM. So you would think that this is a clue that there is something more than just the MSSM. So the MSSM does not answer this question, but you can extend the model, and people have extended models and tried to address the mu problem. So there is a vast literature on trying to address the mu problem and trying to solve it. So of course I won't go through all of the details, or I won't even tell any of those, but you can look that up. So if you're interested, this is something that needs a solution in my view, and almost everybody will agree with that. But this is only in some sense an aesthetic problem because of something called the non-renormalization theorem. So it says that if some superpotential parameter, if you set it to be some value, radiative corrections will not give uncontrolled corrections to it. So it is radiatively stable. So there is no problem. I mean, if you can always put the mu to be of the weak scale by hand and then satisfy this relation without fine tuning or anything, and it's completely fine. It's only an aesthetic problem that why do you have to pick a superpotential parameter or a supersymmetry preserving parameter to be of the weak scale? We saw that the weak scale should come out of the theory, right? Because of RG running, because it is a log running, it takes a long energy desert in order for that MHU squared to go negative, and when it goes negative, Electroweak symmetry breaking. This kind of understanding is very nice, but this obviously is a cheat, right? You have to pick right from the beginning mu to be of the Electroweak breaking scale. So you have snuck in the Electroweak symmetry breaking scale into the thing, and you're pretending that everything, that the theory gives you that. So it is a cheat, and then if you can solve this, then that will have the nice property of not having to put in the Electroweak scale. It just comes out of the theory. So just keep that in mind. It is a big problem if you ask me, and many models have been constructed in order to address this new problem. Okay, so let's look at any questions about this. So I just went through this thing and wrote down the relation just to highlight that there is this hidden problem in the MSSM that you should be aware of. So let's just look at the physical states. So we have two Higgs doublets, right? Which means 8 real degrees of freedom, right? So there are 8 Higgs scalars in the theory, real scalars. So 3 are atom. I hope you know what this means. So it's just that you can go to unitary gauge and gauge away these things, which will become the longitudinal polarization of the W and the Z. So 3 of these scalars, the goldstones, will become the longitudinal polarization of the W and Z, exactly like how the Higgs mechanism works in the standard model. And then it will leave 5 physical scalars. Eight minus 3. So that many physical degrees of freedom, which you can hope to observe. So they are usually denoted as H0, H0, and then H plus minus, and then 8 or A0. So 2, 3, 4, 5. So these are scalars. And this is a pseudoscalar. So this is the Higgs content, physical content in the MSSM. So it's very common to talk about the decoupling limit. Which just means that you have taken parameters, these parameters that we are talking about here, in such a way that MA is much, much bigger than MZ. So why is this talked about? It is just that in this limit, you can show that this lightest neutral CP even Higgs scalar, let me call it H0. It's just by convention, like you denote the lighter one as H0 and the other one as big or capital H. You can show that this H0 behaves like a standard model Higgs. So all the couplings and its couplings to fermions, gauge bosons, everything will be like that of the standard model in this limit when you take MA much, much bigger than MZ. And that's part of the decoupling limit. So in principle, supersymmetry could have had its lightest Higgs behave very differently. Couplings, it gets a mixing angle, and so the mixing between these two. So it can change all of the couplings for fermions and gauge bosons and so on. This is only the combined thing should be such that it should be V, but how it shares the couplings is a free thing in MSSM. And so it could have come out different, but we know already from the LHC if the observed 125 GeV object is really the lighter one, then we already know that it should behave very close to the standard model. So probably it's like still errors are somewhat large, so maybe of the order of 20-25% still. So we are not sure yet, but it's already telling us we should be going closer to the decoupling limit. So there are no large deviations from the standard model couplings to the extent that we have probed already now. So of course the LHC in the next run will reduce the error bars. And so if there are any deviations in the light Higgs couplings, it will show up. If not, we'll go more and more into the decoupling. It's not easy. I mean, it's not hard. So there's big parameter space where this naturally happens. So it's not a cause for worry or anything. It's just that you'll just be picking out regions of parameter space where the lighter Higgs looks more and more standard model-like. So it's just possible in the theory.
In this limit, all the other Higgs are also very heavy.
Yeah, yeah. So all of these are heavy.
And they are order of magnitude. Their mutual order of magnitude.
Yeah, I think so. I think that is true. I'm not 100% sure, but yeah. So all of them decouple. So we can diagonalize, so there will be mixing terms. So in order to define these mass eigenstates, so this is just, you can write down these are the waves, and then you mix. So you just take these interaction states that you had, and they'll have off-diagonal terms, obviously, so you'll have to diagonalize that. And this is a mixing matrix which diagonalizes that HUHD, and these are the mass eigenstates, H0 and H0, which is what I've talked about, right? So this alpha is commonly talked about, so that is another thing that will enter all discussions of supersymmetry. There's this mixing angle in the Higgs sector, and so I just wanted to define that. So you can write down what the mixing angle has to be. So you see in the decoupling limit, alpha is going to be very close to beta. So if MA becomes very large, this thing is going to go to 1. So let's look a little bit more about the mass of this Higgs. How does it come about? What is the mass of the Higgs? Is there any constraints on that? Can it be anything? In the standard model, Higgs mass is arbitrary, right? It's just related to the quartic coupling, lambda. In the standard model, it's a complete free parameter, so I can take the Higgs mass to be whatever I like. I just need to fix lambda. As in supersymmetry, that's not true. The lambda is really given by the D term. So the Higgs quartic comes from the D term, so it is related to the gauge coupling. So it is not a free parameter. So what is the value for the Higgs mass that supersymmetry predicts? Because we know the gauge couplings, right? We have measured the gauge couplings in the standard model. It's not free for us to change. And so you put in those values and you will predict Higgs mass. It's not a free parameter. So what does it come out to be? Is it in agreement with the experiment or not? So at tree level, you can write down the inequality. So you just take this potential we have redefined a bunch of things. You take into account all of that, mixings, all of that, and then you will find that this relation should be true at tree level. So the Higgs mass is lesser than mz times cosine 2 beta. I think this is true in the decoupling limit. You can do it more generally also. But since cosine of anything is less than 1, it just means mh less than mz. So mz we know is 91 GeV, and then if mh is less than that, that's not good. So we want to identify this mh to be the 125 GeV Higgs seen at the LHC. And even before that, it was known from LEP that the Higgs mass had to be bigger than 114 GeV. So it was no good to say that mh is less than mz. That's certainly not acceptable phenomenologically. So is this a problem? No, one thing you can realize, loop corrections can modify this thing. So this is a tree level value, but we have to include loop corrections before we match to experiment. So important to include so this is at tree level, and now we include loop corrections. So let's say we do it at one loop. So the loop corrections turn out to be very important because of the large Yukawa coupling to the top, right? So we know that it is 1, and therefore this number can be substantial, and it is important to include that before you conclude anything from experiment. So because it's a supersymmetric theory, now we have stop also, the left and right. For the two helicities of the top, you have scalar partners of them, which are the stops, left and right. And so that can also go in, and then you have the A-term contribution. So of course all of them contribute, but we have only shown the top sector because that is the biggest one due to large Yukawa coupling. There will be gauge contributions, everything. You have to include everything for a fully quantitative thing, but I'm just writing the dominant ones. And so if you do these, you will get correction at one loop. So one loop is the dominant one, two loop will be a small correction to it. So if you do things at one loop, it is reasonably okay. But if you want everything down to the few GeV level, then you have to include the two loop contributions also, which people routinely do these days. So as expected, it is proportional to yt squared. And then from dimensions, you can argue that it should be proportional to the m top. And then this is the full thing. There will be a log, as you can expect. And this is the full thing. So the xt is just defined to be at minus mu cotangent beta. This contribution is due to the mixing of the stop left and stop right. I will just write that next, but for now just take it that this is the mixing contribution. So the stop left and stop right are not mass eigenstates, they mix, as I will show next. And the stop 1 and stop 2 are the mass eigenstates. And so this is the one loop correction to the Higgs mass. So if you estimate this, you can easily convince yourself that it can be sizable. It's not incredibly hard to get the remaining whatever you need. So another 35 GeV or something you need from loop corrections. But it's not a typical situation, you can already see, right? The tree level value is saying that it should be less than 91. And then you need another 35, which is almost half of that. So you need 50% loop corrections, which is not typical. Loop corrections are supposed to be small. This is already hinting at the fact that it is not a comfortable place to get such a heavy Higgs. But it's not impossible. There are regions in parameter space where you can get it. But you'll have to go fairly heavy in these top masses for this log to contribute reasonably big way for you to get another 35, 40, 45, whatever you need from loop corrections. So another thing you should keep in mind is the Lagrangian parameter MHU squared will also be corrected at loop level. So if you do the analysis consistently, everything will get corrected, right? So the correct way to do it is to do a one loop effective potential and then minimize that. But I'm just roughly arguing these things. So there will be some log and then plus xt squared by 2 m stop and stop 2 times 1 minus xt squared over 6 m stop 1 m stop 2. So you want this to be big so that you get m. You want to take m stop to be big because you want a large loop correction for this log to be big enough that you get a large correction. But the same thing will also feed into correcting MHU squared. And from this expression, you see that they have to be such that it will give you a light mz, right? So as you raise the mass of the stop, you are increasing MHU squared. But now they'll have to start cancelling against each other in order to not this thing also not to be raising. And that means fine tuning. So you have to fine tune these parameters such that it leaves you the 91 GeV. You're raising the mass of the stop, but you're keeping this fixed, and that won't happen naturally. So there is some tension from having to get a large loop correction and from keeping the Electroweak scale light. So that tension will introduce fine tuning, and already we know that in the MSSM it's somewhat fine tuned. It's of the order of a few percent or something. So it's not a very comfortable place. Already the 125 GeV Higgs that has been discovered is significantly heavy. Supersymmetry MSSM would have been more comfortable with a light Higgs of the order of 100 GeV or so. But already since it is all log dependence, it's not easy to get the other 25 GeV. So you have to raise the mass of the stop somewhat quite a bit in order to get that thing. But it is not a very problematic thing. You know, it's like it depends on how comfortable you are with a few percent fine tuning, but that is the situation. And this causes people to ask, are there extensions of the MSSM that will make this more comfortably be? So hinting, so this fine tuning, some fine tuning. So there is no way for people to agree whether this is a problem or not, because this is more like an aesthetic argument. So if you say that, okay, I cannot live with a few % fine tuning, then it is a big problem. And then you look for extensions. So hinting at So one popular extension is the NMSSM, next to minimal supersymmetric standard model, which introduces another singlet, and then the situation is a lot better there. So that extra singlet can contribute at tree-level value. The tree-level relation is no longer true, so you'll have plus something, and that will already make the situation more comfortable. And so the NMSSM does not have much fine-tuning. So it has its own problems, because you have introduced an extra singlet, you have to deal with it, and there are problems associated with that. But whatever. So that is a very popular extension, and in that context, you can solve the mu problem also. So there are, you can put all of these together. So all of these are hints to perhaps tell us that restricting to the MSSM may not be everything. So there may be more structure, and then you have to be fairly. So a little bit more general than just restricting to MSSM. So these are trying to make the case for that. So one way to do it is to increase the Higgs mass is to raise the mass of the stop. The other way to make it is to make this xt parameter, the AT large. So if you make AT large, then you can also get this part to contribute. And AT large means, as I'll show next, means significant mixing of the stop. So the stop left and the stop right mixing is controlled by the atom. And if you make atom large, then you mix them significantly, which is not a problem. So you have to make sure that you include large stop mixing. But it could say something about SUSY mediation mechanisms. So of course, one way to increase delta mh squared, large m stop 1, m stop 2. It is sufficient to make one of them heavy, don't need both. And then large xt. So we saw that something like gauge mediation will have trouble giving you this large AT, right? So in gauge mediation, the option might be only one, that you have to raise the mass of the stop. Because we saw that at the high scale, AT is pretty close to 0. It is a two-loop generated quantity, which we just put to 0. And so RGE running will not give you any significant AT at the low scale. So you will be stuck with a low value of AT in gauge mediation. And so you have no choice but to raise the mass of the stop. Otherwise, gauge mediation was a very nice framework, because it gave you understanding for why FCNCs were not too large. But now we find that the Higgs mass puts a non-trivial requirement from gauge mediation, which it will not easily pass. So you will have to raise the mass of the stop and introduce fine-tuning. So this is all still not so huge a problem that you have to abandon the theory. I mean, you can perhaps take this as a hint that there is more than what we are just writing down. The MSSM is not the complete picture, perhaps, or it may be, who knows. But it's just saying that there are reasons to, want to stop and think, is this everything? So I'll quickly just mention briefly this scalar mixing that we were talking about. So the mass term for the stop, let me just take the example of a stop. All of the scalars will have similar things, so it will be more relevant for the stop because of the large atom. So you will find that the Lagrangian has this mass term for the stops, and so you see there is an off-diagonal term, and that will cause the mixing. And you can diagonalize this matrix by introducing these angles. Or this angle. So I have taken just for simplicity the quantities to be real, but you can generalize this to the complex case. Instead of this orthogonal matrix, you will have a Hermitian matrix which diagonalizes it. And these are the mass eigenvalues that or eigenstates that I was talking about there. So it's after you rotate these interaction eigenstates, is that thing written. And so you can write down an expression for the mixing angle in terms of the off-diagonal term divided by the difference of the diagonal terms. So I won't write that, but so this is scalar mixing, so all the scalars mix this way, and because these things are the largest for the top, the stop mixing is usually the most relevant. The other things you can ignore. Bottom also, or the scalar bottom mixing may also be big depending on tangent beta. So if tangent beta is reasonably large, then that is also important. So before you work out the phenomenology, one has to do all of this. Make sure you go to the mass basis and then work out the phenomenology. So I'll just mention without actually writing down. I won't bore you with the details. You can look up Martin's review for the charginos also mix. Chargino mixing. So you will find that the Vino, the charged Vino and the Higgsino mix. And again, you can go to the mass basis, you can diagonalize. It will have an off-diagonal term, you need to diagonalize that, and then usually people denote the charginos, the mass eigenstates, as chi1 twiddle and chi2 twiddle. So these will be Dirac states. So here this H twiddle will be H up twiddle and H down twiddle put into a Dirac state. And so this is the chargino mixing. Again, I'll just state. These are Majorana states. So these mix and the mass eigenstates are denoted as chi 1 0 chi 1 through chi 4 0. Those are the mass eigenstates of the neutralinos. So you'll have a big 4 by 4 matrix, mass matrix, which is off diagonal, and you need to diagonalize that and go to the mass eigenstates. Again, I won't write down the thing. You can look at Martin's review for all of the expressions, what the mass matrix, the off diagonal matrix is, and so on. Any questions? Okay. So because this is the last lecture in this thing, so I want to leave you with a flavor of what are the places you can look for SUSY in. And of course, people have already been looking for a while, and so we have not found any yet. We haven't found no signals for supersymmetry, and therefore there are constraints. We know that it cannot be below a certain mass scale, for instance, and I just want to leave you with a flavor for where these constraints and probes come from. So where are the places that one can look for? So this will be the last topic. I won't go through all of the details. I'll just make it a qualitative kind of, if you have not seen this thing before, just to give you some idea of what are the kinds of things people normally talk about. So we'll just say probes. And since we have not seen anything, there will be constraints. So this will just be a qualitative discussion. I won't write down any numbers. I won't tell you what exactly is the bound. So there are huge number of papers, reviews written summarizing what the present status of supersymmetry is with respect to constraints, and what is the next best place to look, and so on. So you can just look at them. I'll just point out a few main categories. So I'll start with flavor observables. So I talked a lot about FCNC constraints. This will be a problem with reference to FCNC and so on. What exactly does that mean? What is an example place where we can see what is going on? So let's start with FCNC, flavor changing neutral currents, right? SUSY particles contribute additional sources for FCNC. So there will be new contributions from SUSY particles which will modify these processes. So let me take one example. As an example, take B to S gamma. So you have a B quark decays to an S quark and a photon. So this is at the quark level. You can think about it in the meson level. B meson decays to K star and a gamma, and or some other strange meson, and then you sum up all of them and you can compute the inclusive rate for B to S gamma. And we know that in the standard model, the main contribution comes from diagrams like, I'll just make it representative. There are many more that come in, but I'll just give you some representative thing. Let's say we call this some alpha. So in the standard model, this is the main contribution, and of course you radiate a photon from somewhere. Either you can radiate from the quark line or from the W line, and this will be contribution to B to S gamma. And the operator that's relevant, you can write down an effective Hamiltonian with the Wilson coefficient times the operator. And this operator for B to S gamma is given by B bar and then the flipped also, right, left, flipped, which will be in the emission conjugate. So I've written for BR and S flip, but you can write the flipped one also. The flipped one is not important in the standard model. Anyway, let's not get into that. So, so this thing I somehow or so here, the thing is V alpha B, and here it is V alpha S. These are the CKM elements at these vertices, and of course there is a G2 which I have not written, the gauge coupling. So this thing is proportional to V alpha B. One of them is star. V alpha S star. The amplitude is proportional to that, and the rate will be proportional to the square of that. Okay, so this is the contribution to B to S gamma in the standard model, and this has been measured to quite good accuracy, like at the 10% level or something. And it agrees with the standard model prediction. You can compute this rate, and you match with the experiment, and you find that it is in good agreement. Now, the problem is supersymmetry will also contribute to this. It has its own particles, so it will also contribute. Now, if it contributes too much, then it will be a problem, because I told you that the standard model is a good fit to the data. So any extra thing will be constrained. So, and what are the contributions? Let me just write it there. So I'm just taking B to S gamma as an example, but you can have K bar mixing, K0 bar mixing, B0 bar mixing, anything, a whole list of things, potentially anything could give you a very strong constraint. And you're supposed to in the end include all of it and then ask, can supersymmetry live or not, right? Now, SUSY contribution to B to S gamma. Again, we are taking B to S gamma as just an example. I don't mean this is the most important thing necessarily every time or nothing like that. It's just an example. So now I can take so there are various contributions. So I'm just again taking some representative ones. And of course you radiate a photon from somewhere. So this is a chargino and this is a scalar. So in supersymmetry we have these particles, and in the MSSM you will find that these interactions are there, and this is given again by gauge coupling, right? These are gauge coupling. And what do I mean by this cross? It means an off-diagonal entry in the mass matrix. So you go to the in the scalar mass matrix. So you go to the basis in which the standard model fermion mass matrix is diagonal, that is the mass basis, right? For the standard model fermions, and then you ask, are there off-diagonal entries? You imagine rotating a superfield. So you rotate both the quarks and the squarks to go to that basis in which the quark matrix is diagonal, mass matrix is diagonal, and then you ask in that basis, are there off-diagonal entries in the scalar mass matrix? And generically, yes, there will be. There is no reason why everything has to be so perfectly aligned that when you diagonalize the quark mass matrix, the scalar mass matrix also should be diagonal. There's no reason for it. It's a special requirement that you're asking, right? It will not happen. So in general, there will be off-diagonal entries, and that will mediate this thing. If this were to be diagonal, you will not change, right? You cannot change from this bottom generation to the second generation, third generation, second generation. You will not change. So anytime there is this kind of an entry in the mass matrix, which is a 2-3, some 2-3 element, if it is non-zero, in up-type sector here, you will mediate an additional, or you will introduce an additional contribution to B to S gamma. And so these constraints are very tight, because I told you that the standard model is a very good fit. So you can constrain these off-diagonal entries, and that will impose some non-trivial requirements on the SUSY breaking and mediation mechanism, that they should not mediate too big of this off-diagonal entry.
If had been that there was no
Yeah.
then this cross comes to the
That's right. So one way to suppress this is to make this Ij make it proportional to the identity. So this just means if you start with this this thing and then you rotate to go to the standard model mass basis, because it is proportional to the identity in the left and right, they will remain proportional to the identity, because it's the rotation just cancels. But the problem you have to face is also RGE running. So even though you start with this at the high scale, there will be some slight off-diagonal things. It's not a huge problem, but enough to cause problems in these experiments, because these are such precision probes that even though small things the experiments can be sensitive to that. So one has to check that that thing is satisfied. But it's not a huge problem. If you set it to be flavor diagonal at the high scale, the violations at the low scales are not too big. There is another thing, so mediated from the atoms. So these are things like BR. Let's say I could write down a gluino contribution. So this comes from the atom, the B right S left scalar terms. So the atoms, you remember, were things like right? The Lagrangian contained the soft breaking terms were in that. So I and J are just generation indices, and here I'm just picking the 2-3 of this general atom. And so they always, when I put HD to its bev, it will just give me a mass bilinear. It will just give me an off-diagonal term. And these things can now induce flavor violation. So one way to get rid of this is to make the ansatz that Aij is proportional to lambda I. Again, this is bizarre, because this is a SUSY breaking parameter and this is superpotential parameter. So it's not a priori clear why they should be related, but perhaps there is some symmetry or something which relates them, and like whatever. If you just make this ansatz, then if you go to the standard model mass basis, automatically this will also be diagonal in that basis, and you will not mediate this kinds of flavor violation. So doing this is called MFV, minimal flavor violation. So there is still some, in the end, only contributions that are proportional to CKM not these additional sources. So you can just write this thing, and in the MFV prescription you will make this proportional to the same quantity. So this is the most minimal flavor violation you can have, and that goes by the name of minimal flavor violation.
So this condition for priming
Yeah.
8, sorry, 8. So is it realized in this
No, we had to make that ansatz. So M-Sugra, yeah, did not have either of them. So supergravity does not have either of them. It does not really respect, it doesn't know about flavor, it will just intuit some generic A and some generic M0. It does not care about standard model flavor structure and all. But we just, in doing M-Sugra, in supergravity it does not care, but in doing M-Sugra, we just ad hoc impose that this be true and this be true at the high scale. For this reason. Otherwise, it will be so bad that you will not live, that model will be dead. So, just phenomenologically motivated, you just made that answer. So, these things generically go by the name, like generically speaking, these things are large contributions, and we have no idea why we have not seen it. And this goes by the name of the flavor problem in supersymmetry. So if we should have already seen it long time ago in flavor observables. But again, you take this problem to mean that this is a hint that perhaps flavor is somehow connected to all this. You cannot write down supersymmetry breaking independent of flavor, so you have to include flavor in the full theory and make sure that the full theory leads to these kinds of things, that it knows something about flavor. You cannot make that completely independent. So I was looking at flavor changing neutral current. So let's just consider some examples of flavor diagonal probes. So I'll be very qualitative. So one example is G minus 2 of the muon. Here you don't change the flavor, you just look at properties of the muon. So the operator that's relevant here is that, and so you are asking for things like that. Right? So you radiate a photon from somewhere. And these are incredibly precise measurements. So this is known to some 8 decimal places or something, the G minus 2 of the muon. And so any small contributions due to supersymmetry can really upset this thing. And one contribution in SUSY, this is standard model, for instance, or some example thing. I don't even know if that is the biggest contribution, but so again, you can have the charge contribution. So these will be extra sources that will contribute to G minus 2 of the muon. And because it's such a precise measurement, you can put tight constraints on it. Interestingly, this has some 3.8 sigma deviation or something. So this G minus W mu. This was experiment done at Brookhaven, so it still stands. Now the machine is all dismantled and shipped to Fermilab. So Fermilab is now going to continue this thing and try to see if they can improve the precision. But the challenge here is hadronic corrections. So it's incredibly hard to reliably estimate these hadronic corrections, and that's where the problem lies. You cannot definitively say that it is in fact some new physics that is contributing because of this uncertainty. But supersymmetry can explain this thing, can explain this deviation by these kinds of extra contributions. So it's interesting to see how this develops. So another example of a flavor diagonal is electron EDM. So I took this thing, this is a real contribution, and if you take the imaginary part of this operator, you will induce EDM. I guess there is a gamma 5 here. So this is the EDM operator. So again, is imaginary part of this kind of diagram. So you'll again supersymmetric particle, if they have phases, because you're taking the imaginary part, phases will be constrained. And these are pretty tight constraints on phases. So again, the way to escape this is to set the phases to 0. And we don't have a reason to do it. There's no good reason why those phases, which could in principle be there, why should it be 0? We don't know. So, but we will be forced to set those phases to be 0. And this is again a problem. Perhaps some deeper theory will tell you why those phases have to be 0. All of this is probably hinting that we have not written down everything there is to write down. There's, if there is some experimental observations, it can guide us to go forward, but otherwise there are so many possibilities that you don't know which way to proceed. But all these are indicating that perhaps we don't have the full theory yet. Okay? So last thing, 5 minutes I'll spend on how do you look for supersymmetry at the LHC, direct observation. So I'll be done in a couple of minutes. So this is a vast subject. I by no means will do justice to it, just to give you a flavor for what are the kinds of things. So first statement is so far only limits. This is very disappointing. So many people expected that in the first run itself supersymmetry will be found at the LHC, but it does not. So it has put some non-trivial limits. So let's consider R parity conserving theory, or in other words MSSF. So the signatures qualitatively change whether you look at R parity conserving theory or R parity violating theory, and that's because of LSP has to be produced and exits LHC as missing it. So this is a heavy object, we think. We don't know for sure, but what everybody canonically analyzes is LSP, which is of the order of few hundred GeV. So that massive of a particle, if it exits the detector unseen, it will produce characteristic signals of all of the other visible stuff. And you can look for those characteristic signals. So for example, so at the LHC, things that have color will be produced with the largest cross section because it's a hadron machine. So you start with colored initial states. So you can pair produce Bluino, for instance. And then, let me give myself some room. So gluino gets pair produced, and then one example decay, there are many possibilities. So I can go to a quark and a quark, and then this then goes to a quark and the LSP. You see that in the end of this is called as a cascade decay. So at the end of this chain, there has to be the LSP, because R parity has to be conserved. This is R parity minus 1, this is R parity minus 1, this is R parity minus 1. These are all plus 1, right? So R parity is conserved, and neutralino has to be produced, and this exits. This is a massive object which exits the detector as missing energy, and the visible thing, these two jets, is what you can measure. So of course the other gluino also will do its decay, so you will have both of these present, and you look for these signatures. So another possible signature of the gluino decay is goes to a quark, and then quark goes to some other quark, Q prime, goes to chargino, then neutralino, and then W, and then let's say L nu. So this has two jets and one lepton, and missing energy due to the neutrino and due to the LSP also. So you can look at a combination of this. So usually people look at jets plus missing energy channel, the jets plus few leptons plus missing energy, all of these channels you look at, you compute the standard model background to them, and then you ask, is there a deviation from the standard model computed rate that has been seen? And if there is a deviation, then you can interpret that as something like this happening. So that is the way to look for it at the LHC. So that is gluino pair production. So there are many other colored particles also. For instance, stop is one thing that you can pair produce. So we can again look at pair production of a stop, the lighter one, which then decays. So you can go to a bottom and a chargino, then it decays to LSP, and then W and mu. Same way the other stop can do something else or the same, and then you have this as a signature. Again, you do the same thing. You have missing energy, you have a B quark, and then lepton. So you look for those channels, and then you ask, is there an excess? You can pair produce bottom, which then goes to, let's say, B and neutralino, or some longer chain. So which particular decay chain and by what is the branching ratio, all of this depends on the mass spectrum. You know, if this is very heavy, then this rate will be suppressed because it will become a three-body final state, and then the branching ratio will be small. But if it is accessible, then you will produce it at reasonable branching ratio and so on. So last thing, I'll just close in 1 minute, you know, like dark matter detection. Can also tell us if supersymmetry is there, because the LSP is a good candidate for dark matter. So you can either look for it with indirect dark matter detection, which is basically some annihilation of the neutralinos in the sky. So for instance, some fermion can mediate this thing to give you FF bar final states. You then point a telescope in the sky, and then you ask, are these fermions being seen in the sky? And this will be the halo. Our galaxy is thought to have a dark matter halo, and so these decays or annihilations could be happening in the galaxy, and we might be able to detect an excess of a background of these fermions. These are called indirect dark matter, or there could be direct dark matter detection, where you make a sensitive detector on Earth and then ask whether or look for a neutralino interacting with that detector. And you measure the recoil of this nucleus. This could be a Higgs, for instance. So you look for a recoil of a nucleus, very sensitive detector, and if there is a dark matter halo where we are, it should give a kick to this nucleus, which you then measure. And there are very sensitive experiments looking for that. All of these have not found anything, and they are in a very interesting region where they are probing a big part of the parameter space based on all of these constraints and requirements that we put. These are very interesting experiments to keep track of right now, and any one of them could potentially see a signal unambiguously. There are hints always, and it's not clear whether they are real things or experimental problems or experimental uncertainties and so on. But they're all getting to a region where things are very interesting, and it's exciting to see if any of these experiments will find supersymmetry or some new physics, which you can then try to ask what is the new physics that we have seen. But so far, nothing conclusive. Okay, yeah. So can we just stop?